Hi all, let us continue with class 13, reactions at the alpha carbon. In this video, I'm going to describe the alpha halogenation of an aldehyde or ketone via the enol. Here we have a ketone, and we could use these reagents to put a bromine on the alpha carbon. To be able to do that, we are going to go through the enol, meaning that there has to be an alpha hydrogen at this carbon to form the enol. You notice that on this alpha carbon on the left, there's no hydrogen to remove, and we cannot create the enol on the left side. We could use this reaction to put a bromine at the alpha position of aldehydes, ketones, and I should have also said other carboxylic acid derivatives like esters and amides. I do want to jot down a couple of notes before we get started, and then I'll show you the mechanism. When recalling this reaction, I want to remember that the first step is the rate determining step. This reaction actually goes through a general acid catalysis, and I'll point that out when we get to that. Most importantly, I want to remember that it goes through the enol, because a lot of reactions that we are looking at in this class, we actually go through the enolate, the anion of the enol. But in this case, we do not get the enolate anywhere in the mechanism, but we do go through the neutral enol. The first thing I want to show is the first step. There is a lot happening in the first step, in the rate determining step. I think it's useful for you to see the order in which I draw my mechanism arrows. I do have 3 reagents here. Oh, by the way, this is acetic acid, the abbreviation for acetic acid, and I've have it drawn up here. So the first thing is we take water as a base and we remove the alpha hydrogen. So you could put the bond on this carbon to make the anion. You've seen that happen. You could make the double bond and put this pi bond up here to make the oxygen anion, but in this particular reaction, look what happens. We're going to use a general acid catalysis, and we'll still make the double bond, but now I'm going to use this pi bond to grab this hydrogen, because we're never going to make the enolate. Can you draw the result of my mechanism arrows? We have now the OH. We have the enol, right? We did create, what did we create? H3O plus this anion, the acetate anion. We're not going to be using a very strong acid. The acetic acid is a weak acid, and it does go through a general acid catalysis. This is the rate determining step. Let me write that for sure. The slow step. And let me remind you how I remember the difference between general acid and specific acid catalysis. The hallmark of specific acid catalysis is what we all learned at the very start of Organic Chemistry 1, that you protonate the carbonyl first in one step, and then you do the rate determining step, whether that is attacking the carbonyl carbon or deprotonating, in this case, the alpha carbon. The thing you want to look for is that, does the catalysis happen at the rate determining step like we have here, or does it happen pre-rate determining step? That's the main difference between specific acid or base catalysis versus general acid or base catalysis. You know, if this was specific base, then we would deprotonate first and then have the rate determining step. So it all depends on whether the catalysis is happening in a separate step, right, from the rate determining, or in this case, it happens at the same time. So let me write that down. because the rate determining step happens at the same time of the protonation, we actually never see, right, the protonated carbonyl. Again, general acid, the protonation, well, general acid catalysis, protonation happens at the same time as the rate determining step. Specific, separately. Okay, I don't want to belabor the point. Another thing to realize, and we knew it here from our bullets, we formed a neutral enol, right? Neutral. Okay, so I kind of messed up my spacing because I got to figure out how to continue the mechanism, because the next step is going to be pretty simply attack the BR2. So give me a second, let me figure out how to do this. We'll keep everything at equilibrium, and that's going to be important when we talk about kinetic versus thermodynamic later in this video. And the mechanism that I want to use is, the mechanism arrows are, remake the carbonyl, grab that bromine, break this one off, and I think we're very close, right, to our final product. All we have to do is worry about deprotonating that carbonyl. Bromine here, plus Br minus. Now, yeah, we do have the protonated carbonyl here, but again, this is way after the rate determining step. Not way after, but it's after the rate determining step. You know, the step right here is fast, and the last deprotonation will be fast as well. And we have that. We could use the water, or we could use the bromide. And that is also at equilibrium. We have the bromine at the alpha position. We did create some HBr. And just a reminder, there's your alpha. And I know I forgot another methyl group. It's important that we had this tert-butyl group here because I didn't want to form the enolate on the other side. I wanted to specifically form on this side. That's the full mechanism. Okay, and let me just label this as fast as well. Could this have been predicted that we are going through a general acid catalysis? Possibly. We're using a weak acid. Okay, so if we use a very strong acid, then we would probably protonate first before the rate determining step. Another thing we could say is that the other steps in the mechanism are fast, and I think I'll leave it at that. So we don't have to predict that it will go through general acid catalysis. We just have to know that it does and how to show it. Now I have a couple examples because there was no ambiguity here. We were forming the enolate. I meant the enol with a double bond on the right. But what if we had a choice? Let me give you this other example. Okay, in this example, we have two alpha carbons, and depending on which one forms the enol, which alpha hydrogen we remove to form the enol, we'll get two different products. If I remove the alpha hydrogen on the left, then my product would have the bromine on the left. And if we removed the alpha hydrogen on the right, then the bromine will be on the right. Why don't we remind ourselves of that fact, looking at our general example. I remove the alpha hydrogen on this carbon, correct? And that's where the bromine eventually ended up. Okay. Which alpha hydrogen is more acidic in this case? Maybe that's not the best question. The better question is, are we forming the thermodynamic or the kinetic product? What I should have emphasized up here is that everything is at equilibrium. And when your reaction has a chance to go through equilibrium, when there's reversibility, okay, and I mean significant reversibility. Okay, not just I don't know what it's called, micro reversibility, but we do have reversibility. Then typically your reaction is going to head towards the thermodynamic product. What is the thermodynamic product in this case? Well, we go through the thermodynamic enol, and that's the enol with the carbon double bond that is more substituted. Therefore, the enol that we are going through to make the major product would be this one. And let me put it in brackets to indicate that it's an intermediate, and therefore it is headed towards that. We remove the hydrogen off of this alpha carbon. We could call this the thermodynamic enol, and it's the enol that has the more stable carbon-carbon double bond. We call this tetrasubstituted. If the double bond was on the right, that would be trisubstituted. We have one hydrogen here. The other 3 spots are occupied by a non-hydrogen. Okay. There's one more example. I was trying to figure out what is this reaction useful for. In this example, I'm starting with an ester. I marked the alpha carbon, and I gave you a couple of reactions. Obviously, the first one is the reaction we just went over, brominate at the alpha position. And then we have ammonia, okay, reacting with that alkyl halide. And then we have conditions for hydrolysis. Can you predict the product if this starting material was put through these 3 reactions sequentially? The product that I would get looks like this. Does that look familiar? We have a carboxyl group. We have an protonated amine in this case. We have a R group coming off of the alpha carbon. This is an alpha amino acid. I'll let you work out the intermediate products, but again, number 1, alpha-halogenation. Number 2, I would say, is a substitution, SN2. The ammonia comes in and kicks out the bromine. Number 3 is hydrolysis, to hydrolyze the ester into the carboxylic acid. Since we're under acidic conditions in the last reaction, we do protonate the amine.